Hi there, and welcome to Raelene Math. In this video, we're going to take a look at why a corner is not smooth. So smooth means differentiable, which is able to have a derivative or able to be differentiated. The derivative is the tangent slope, so it really means that we have a defined tangent slope. That means when you zoom in on a graph, you've got one single tangent line, and that line isn't vertical because the slope of a vertical line is infinite. So the first thing that has to be true if a function f is differentiable at a point is that the function has to be continuous. We have to have a point that's connected to other points on the graph where you can zoom in at that point of tangency. And then once we do zoom in, that tangent line that we get has to be a single tangent line with a finite slope when we zoom in far enough. So a corner fails to be smooth or is not smooth because the left and the right hand slopes are finite numbers. We don't get vertical tangent lines when we have a corner, but we don't get a single tangent line because we get two. Let's take a look at a difference. If we have a function that is smooth, let's say sine x, if we zoom in at the origin, if we zoom in far enough, eventually that curve looks like a line, and that is the tangent line whose equation is y equal to x. So if we have the regular zoom, the purple graph and the blue graph look different, but if we zoom in far enough, the purple graph and the blue graph look the same. In other words, the blue graph approaches the purple graph. Its tangent line. So let's take a look at a corner. A parent or basic corner function is y equals the absolute value of x. And if we zoom in far enough at the origin, that graph just never looks like a single tangent line. And so we see that there are two different tangent slopes on the left-hand side and on the right-hand side. The left-hand slope is -1 because this line is the line y equals negative x, and the right-hand slope has a value of +1. Those are both finite values, so the slope doesn't fail to be finite, but it does fail to be a single value. So there's one point I want to clarify though when we think about corners, because we think of this corner every time we think of a corner. I want to show you a corner that doesn't have a minimum or a maximum point, namely this one. Here's a piecewise function that I'm making as a corner, except I made it for the wrong x values. It's continuous because I'm making it connect at the origin. However, the graph in purple increases and the blue graph increases. When we zoom in, so we can see that there's no maximum or minimum there. When we zoom in at that corner, we can see that the function still never looks like a single tangent line. We have a +2 slope for the purple piece and a +1 slope or derivative for the blue piece. But my point here is to emphasize that because the graph doesn't turn around and change from increasing to decreasing or vice versa, that we don't have a max or min. And so not every corner is going to give a max or a min. Okay, so now that we have this parent corner graph, we can take a look at algebraically why this piecewise function, this parent corner graph, fails to have a derivative at the origin. We have the piecewise function defined as follows, and when we come up with the derivative function, we are going to take the derivative of the left-hand piece, which is the derivative of negative x, which is -1. We have established that the derivative does not exist when x is equal to 0 because the derivative fails to be a single value. And when x is greater than 0, the derivative of x is +1. Now we can see this on the graph over here. If we plot a point on the original function at -3, 3, we can see that there's a tangent line here when we zoom in, which is the same as the original line, and that has a slope of -1. So I'm going to plot the ordered triple as x, y, m tangent. And I see if I pick out the x coordinate and the m tangent value, which is what I plot in the derivative function, I'm going to plot the ordered pair -3, -1 over here. So -3, -1 is the x coordinate, the slope of the original graph. In other words, the height of the derivative is the slope of the original. The height of the derivative graph, the y-coordinate of -1, is the slope of the original. And we can do the same thing for a point over here. Let's say at 2, 2 would be the x, the y. And if we zoom in, we get a tangent slope of +1. And so if we pick out the x, m tangent and plot that point over here, 2, 1 would be the corresponding point on the derivative graph. So now we're just kind of comparing the numerical and the graphical, but we really want to get to why algebraically this derivative doesn't exist. So we do know that f of x is a continuous function, and so we are going to go on to the second condition. After the function is continuous, we have to have that the derivative exists. And the derivative f prime of 0 is defined as a limit, and it's defined as the limit of a secant slope. And so I'm going to use the definition of f prime of a as the limit as x approaches a of f of x minus f of a all over x minus a. Now what we're really saying is that this limit has to exist, so the limit has to be a single value, meaning that the left value of the limit and the right value must be the same, and the limit must be finite. So let's first work out the left-hand derivative. I'm going to call it left-hand derivative or left-hand slope, and I'm going to give it a notation of f prime. We're evaluating the slope at 0 because that's where the corner exists, and I'm going to put a 0 with a superscript of minus. Now what this means is the limit as x approaches 0 from the left of the secant slope. And I'm just going to remove these here so I have a little bit more room. And we recall that the secant slope is given by y2 minus y1, so f of x minus f of 0 all over x minus 0. Now f of 0 is specifically the y-coordinate when x is 0, and on the opposite value graph that's 0. So I don't need to write that down, and I also don't have a 0 here. But then I need to use the correct piecewise function definition for f of x when x is less than 0. And so when x is less than 0, I use negative x. And so this gives me a limit of negative x over x as x approaches 0 from the left. Now normally this would give me indeterminate when I directly evaluate this rational fraction, but I can reduce the x's and be left with the limit of a constant negative 1, which is equal to negative 1. Now this represents the m tangent on the left-hand side. And that's to just the immediate left of the origin. And in fact we had a derivative or a tangent slope of negative 1. So the next thing we want to do is to work out the right-hand slope or the right-hand derivative. And so the right-hand derivative we will write as f prime of 0 plus. We will work it out as a limit. So the limit as x approaches 0 from the right of f of x minus f of 0. Now, just because we are working out from the right or from the left doesn't mean we use a different function definition for f of 0. Recall, f of 0 is a function value. It's what y equals when x equals 0. So it doesn't have anything to do with x being less than 0 or x being greater than 0. Simply we substitute the function value for both pieces, whether it's the left or the right-hand derivative. And in each case that value is 0, and then we substitute the rest here. So the limit as x approaches 0 from the right, f of x for the right-hand side or the right-hand piece was defined to be x. And so we get x over x. If we directly substitute we would get indeterminate, but we can reduce this fraction and then we get the limit of positive 1 as x approaches 0 is still positive 1. And we notice that the m tangent on the right, immediately to the right of 0, is positive 1, and the m tangent to the left is negative 1. So the two left and right hand slopes are finite numbers, but they're different. Now remember what we said a moment ago, that the height of the m tangent graph is the slope of the original function. So if the left and right hand slopes of the original function are different, then the left and right hand heights on the derivative graph are different. So having two different and finite slopes on the original means we have two different and finite heights on the derivative. Two different and finite heights means we have a jump discontinuity. Two different and finite slopes mean we have a corner. So there you have the rule of 4 graphical, numerical, verbal, algebraic connection about why a corner is not smooth. If you like the video, click like, leave me a comment down below, and don't forget to subscribe. Thanks for checking out Raelene Math.